Hello and welcome to this presentation where I'll take you through a slide deck that was presented at the aapg in Melbourne in 2015 by myself. I work for GISPAX, and Jeff Brown from Rose & Associates. And at that conference we presented this pack that basically said why bother? Why bother with play-based exploration? It's a pretty common question that comes up, so we thought we'd actually do a paper on it. So this will take around about 45 minutes to an hour, depending on how much talking I do. And please send us comments if you have any questions. The abstract is included. This is the abstract. It's a bit wordy, and the presentation material is available on the aapg Search and Discovery website. So first of all, let me explain what Player is. I helped develop Player 8 years ago. It's an extension in ArcGIS that does conventional and unconventional play mapping and play assessments, and all the data saved to an industry standard database. It's 8 years old, and we've got about 30 plus global exploration and production companies. And we see it as the benchmark for play analysis software available on the market. We're not trying to compete with prospect tools, and we have aspects of the Player suite which have been developed to evaluate both unconventional and conventional exploration types. Player, the core tool, is particularly well suited to evaluating large complex basins with multiple play levels and lots of fields. But it can easily be applied to frontier, unproven basins with limited data and no discoveries. In both settings it has a very well defined workflow, and we've designed it to try and make using ArcGIS easier for the coalface geologist. It is not a specialist tool. Both Jeff and I worked in large companies. I worked in Shell and other companies, as did Jeff. And the last thing most teams need is specialists coming in, doing some work and then disappearing for a year. This is the opposite of that. This is a very simple tool designed to be worked by the people in the teams. The unconventional aspects of Player can generate both qualitative and quantitative evaluations, and we try and capture the knowledge in your company in a workflow format. I'm not going to present on that in this presentation. And the question always comes up, why is Player in ArcGIS? And the simple answer is because the platform actually does matter. ArcGIS deals with spatial objects, polygons, better than any other software package. The objects are spatially aware, so if I want to go and get a value from a well and from a play map, from a numeric play map, it knows where everything is and it's easy to do. There are no grids underneath the polygons, and it's a proper GIS. So what I mean by that is when we bring data in, we don't have to tell it what the projection is. It automatically projects in the right place. There's about 30 million licenses on the planet, so it's a very widely used open platform. And over the last 30 years or so, it has a whole series of functions and tools in Arc objects and other parts of Arc that we use as part of the Player toolkit. And that's why we don't use a shareware GIS. They don't have those tools behind them. And it's very cheap. Our license will probably cost $1,000 or $2,000 in most parts of the planet. So it's now the industry standard platform. Every regional team that I go to around the world uses it. They don't use anything else. And we've designed Player to sit on flat file versions on networks or PCs. And we've also got a version that talks to Oracle and SQL databases. And the bottom line is we could not do the play analysis work that we do on any other platform. So it's there for a reason. So this talk is focused on conventional oil and gas, not unconventional. Both ourselves and Rose have solutions for the latter, which we're not going to talk about today. And let me also give credit to Jeff, who I've worked with over the last 5 years or so, and give him contributions for a lot of the learning that I've picked up over the last few years. So, why bother? Let me take you through a very, very simple example. Here we have three prospects, A, B and C in yellow. The probability of success and the success volume, if it's successful, the estimated million barrels of oil equivalent that's going to be found is shown on the table and also on the yellow blobs. And you can see that prospect A is above the proven source kitchen, and it's surrounded by the fields in red, so it's very close to some discovered resources. Then there's three black dots. These are the dry wells. And then over here we've got prospect B and prospect C. And the question is, which one would you drill? How would you evaluate it? And the simple answer is that as an industry, most of us would simply multiply the chance of success by the volume of success and come up with the risked volumes. And in this case, the largest number is prospect A, which sits over here. Now that prospect also happens to be close to the fields. The assumption here is that the drilling costs and the value are all the same, etc., etc. So we're using risk volume as a proxy for value. But most companies would make that decision and feel very happy with themselves that they've actually got that evaluation correct. And so my question to you is that the correct decision? So let's look at this a slightly different way. Let's now put on some migration dividers, some polygons. And on the left, where prospect A is, we have the fields and we have the source rock. And all of these fields and prospects are in the same play. That goes without saying. And obviously this area here all has proven charge. So we would expect prospect A to be in a polygon with proven charge. But once we go beyond this limit into this area beyond the three dry wells, then we come to an area, and we've made an evaluation here that there's a 25% chance that we can get hydrocarbons into this polygon, that is possible, and get hydrocarbons to prospects B and C. So it's quite a simple concept. I'll come back to the details about these wells later, because obviously why they failed is significant, and obviously these are just dummy numbers. So if we now drill prospect C and it's a discovery, what happens? So let's go through the thinking of the maths. So if I drill prospect C, I've got a 20% chance of finding 30 million barrels. So on a risk basis, I've got 6 million barrels of oil equivalent. And that's what happens in isolation. And that's the standard way of looking at a decision tree for drilling a well. But what also happens here when we drill C, and it's a discovery now, is that clearly we've now migrated hydrocarbons through this area and effectively de-risked prospect B. So that's clearly an impact of success at C. So how does this work? This was the C evaluation by itself. And if I look at what's happened to B, before I drilled it, I had a chance of success of 10, a mean volume of 50 million barrels and a risk volume of 5. After I have success at C, I've proven the migration. So my migration estimate goes from 25 to 100, and the chance of success now would be 40 instead of 10. The mean success volume hasn't changed, and my risk volume now is 20 million barrels. I haven't drilled it, I haven't discovered anything, but it's clearly now a lot better. So the incremental increase between the 5 million barrels and the 20 is 15 million barrels. I've got an extra 15 million barrels that I didn't have before. But that 15 million barrels only happens 20% of the time when I actually have a success at C. So I multiply the 15 million barrels by the 20% of the time that it actually happens, and I can add 3 million barrels of oil equivalent to the 6 from prospect C to end up with a total of 9 million barrels of oil equivalent. So the maths are very simple, and that's simply going through the logic. So Let's look at another hypothetical. If prospect A works, what happens? Well, I discover 14 million barrels, but there's no impact on prospect B and C. It's in a different polygon, and this result is not going to impact my understanding of the migration risk in this area. What about if I drill prospect B? So here I've discovered hydrocarbons at prospect B, and again, like before, I've de-risked the migration into this area, so that will affect prospect C. And the maths is exactly the same. I drill B and I end up with a risk volume of 5 million barrels. It impacts my valuation of C, and when I go through the same mathematics, I end up adding 1.8 million barrels of oil equivalent, and I end up with a total of 6.8 million barrels of oil equivalent. So when I look at the summary now of those three prospects, when I look at what's going to be delivered, then you can see that now prospect C actually looks like potentially the better prospect to drill because of the de-risking impact that it has on prospect B. So very simple. So what we've done there is effectively share risks between real prospects. And when we do this, it will change what you drill. And that's why we do play-based exploration, and that's why we use numbers. So we need to make maps of those shared risks, and we need real prospect data. And so that's why we do play-based exploration. Now, I'm not saying that prospect C is actually better than prospect A. If your company is in basically a harvest mode, it's probably going to drill prospect A. If it's in a growth mode, it's probably going to drill prospect C. But either way, you can have a sensible discussion with your exploration management about which prospect they would prefer to have in their portfolio and explain the upside of drilling different prospects. That's what play-based exploration is really trying to do. So now I'll take you through the main aspects that come up when people talk about play-based exploration. So these are common subjects that people kind of talk about, and I've been doing this now for about 4 years. And the first thing is, what are the different types of play maps? So this becomes quite an emotional subject. The industry doesn't have a standard way of doing play analysis or play assessment. And really what happens is it depends on the local senior manager and what their background is as to what they perceive play-based exploration is. So traditionally, managers from BP will believe that colours and traffic light maps are play-based exploration, and people from Exxon or Shell will believe that numbers or numeric play maps will be play-based exploration, and they'll argue. Now the answer is, it doesn't really matter. The different maps give you different things, and it's really understanding the geology, not arguing about the colour bars. So let me talk you through the 3 different types, and the most popular one, and the one that I see the most, is traffic light maps. And this is a BP methodology where the different risk elements, or chance elements, if you want to be specific, typically reservoir, seal and charge. Each evaluation is separated into good, medium and bad, which is obviously green, orange and red. And then each element is stacked together to form a composite, a CCRS map. And when that process happens, you only get green where you have green at every level. If you have green and oranges, it will be orange. And if you have red at any level, it will be red. So the process really high grades the areas where all the elements are believed to be present. It's a useful process. So here's an example of a traffic light map from the Ceduna Basin, south of Australia, in the Great Australian Bight. And this is the undrilled play section beneath the TD of the one well that's been drilled down here. And just to put this into scale, this is a massive upper Cretaceous delta where most of Central Australia drained out through this southern area to form this massive delta. So this is quite an interesting frontier area. So this undrilled play, we've done an evaluation based on public domain data, and this will actually be presented at the 2016 APA in Brisbane. So if you're interested, I'll send you the presentation. And you can see here, when we've done the evaluation of reservoir seal and charge, when we make that composite stack, the interpretation is that this northern area, north of Gnarly Knots, is the better area. And that's an area where we're above oil mature Cenomanian source rocks. We've got some tertiary burial that give them a little bit of burial in this area, plus it's an area where the reservoir is not too deep. So it's an overlap of different things, and obviously traffic light maps are thus giving us spatial focus. We would, in a perfect world, now go and look mainly at this green area and not at the red area. It gives us spatial focus. But traffic light maps are relative goodness maps. They really just say, over here it's not very good, over here it's good, and here it's just right. So that's why I tend to call them Goldilocks maps. They are easy and quick, but they do have a few problems. So let's go through some of those issues or problems. And the primary one that I see a lot is that people use grids and then partition them to make them into risk or chance evaluations. And the boundary values that they pick move the lines. So here I've taken an evaluation from the same Ceduna area of reservoir presence, and here I'm using an isopack. And in Player, when we work with grids, we can simply bring in the grid, slide these things up and down, and then it pumps out the different colors. So here I've got the red-orange transition at 500 meters and the orange to green transition at 2,000 meters. But if I slide these bars up and down in Player and then save the output, I can quickly change where the lines are and change what the colors are. So these boundaries between green and orange and red have no geological meaning at all. They are completely arbitrary and they are drawn by the computer. And even though they may be relatively useful, they're not geological boundaries and they're quite dangerous. There's no difference between a prospect on different sides of the orange to the red here. No fundamental difference. So the second issue that you get is when you put real prospects on top of your play map, there's no linkage. So this Springboard prospect here, it's in the orange area or the red area on this map. Does that mean it's a low probability? Is it an area where I don't have much data? It's not clear what this means. There is no linkage between my POS, my COS, my P sub G and my maps. They're not linked at all. The third issue is obviously if I have success at Springboard, then as a geologist it's obvious that I would de-risk the things around them. These must look better if I've got a discovery next door. But there's no way of doing that with traffic light maps. There's no linkages between the prospects. And lastly, when we come to areas with complex geology, and in this case I have an example where we have channelized slope channels coming down to a basin floor fan down over here. It's covered by 2D, it's undrilled, and we have these different lobes that have been mapped out from the data, and we've got some prospects on it. So how would I turn this into a traffic light map? Would I try and put green where all the blobs are, or what would I do with this? How much detail would I do? And a lot of people would use an amplitude extraction and try and pull out a value for every point, which is incredibly dangerous. So it's not clear what to do in areas of complex geology, and I'll come back to other solutions for this problem. So in a summary sense, traffic lights or Goldilocks maps, if you don't have much time or much data and you don't want quantitative estimates, there's nothing wrong with traffic light maps. They will give you spatial focus, but they'll give you very little else. The second most common map that I see is people who put numbers into those polygons instead of colors. And traditionally what they do is they try and emulate their corporate risking, their prospect risking. So in the corporate sense, if they had a prospect, if they had reservoir presence, reservoir effectiveness, trap presence and charge, then they would have polygons for each one of those, and they would be average prospect values in those polygons. And then they would multiply those elements to come up with an overall composite stack. And note here, you have to include trap presence here, because that's what you have in your prospect world. And in most cases here, the boundaries that are used in this kind of evaluation are not grids. They tend to be proper geological boundaries. Now, there is one exception. There is a product on the market that still has a rules-based approach to generate these kind of maps, these P sub G POS average maps. Example would be if I have an isopack which is greater than 200 meters, then make the P sub G for reservoir present 0.8, etc. These rules will be applied to grids and then they will be pumped out. And we would not recommend that approach. Remember, those lines are being drawn by the computer. They're not geological boundaries. So obviously when we have that composite stack, if we've done this mathematics, then there is some kind of link between the prospects and the overall polygons. It's a guide. So one of the biggest problems here is when I have that product, it doesn't really tell us if the plays are proven or not in different areas. So as an example, if I had a prospect in a proven play area, all the elements were there, but I had lots of local risk, it might be a 25% trap risk, I'm going to end up with exactly the same evaluation as something in an unproven area with a 50% play segment and a 50% local risk. So those two things will look exactly the same on this kind of evaluation, but they're totally different kinds of prospects. So we need to do something else. But what these types of maps give you is normally they're geological boundaries, and there is a soft link between the prospects and the overall values. So that third type of play map is what we call split risking. And here you're taking the second type, those average prospect risk polygons, and you're splitting them into two parts. That is the shared and non-shared elements. And this is a methodology that's been used by Exxon for the best part of 50 years. The maps are always polygons and they're always geological boundaries. And the key theoretical thing to learn here is how to do this splitting. If I had a reservoir presence polygon with an 80% reservoir presence risk, and I ask somebody, split that into shared and not shared, we don't get taught how to do that. That is not intuitive. So there's some tricks that you have to learn to actually do that splitting. And every manager, as soon as you show them this methodology, will be concerned about double dipping. They'll think you're going to end up with a lower risk. That's what managers worry about. We call it split risking because that's what we're doing. We're taking the average prospect risk and we're simply splitting it into the two components. We are not double dipping. So the type 2 maps that I was talking about are these average P sub G maps here on the right. And for each polygon, we're splitting it into two components. And then we make three different stacks. The first stack is the shared, the second stack is the prospect specific, and the third stack is the overall average prospect value. So if I have a layer cake situation, very, very flat and infinite reservoirs sealed by extensive seals, layer cake seals, and I have ubiquitous charge, then there won't be any local variation here. And that my play map stack, this stack that I've made, will be identical to my overall average prospect stack here on the right. But in many places I do get discontinuous reservoirs and I do get variable charge and I get variable seals, and there is a lot of local variation. So when I look in those cases at the overall average prospect risk stack on the right here, it's not easy for me to see the fairway. But when I strip away that variation, I can then see the area where I believe that I have the basic elements present. So split risking in complex areas is a very good way of actually mapping out where your play fairways are, and that's one of the major advantages of doing it this way. So let's take that basin floor fan and go through a simple exercise of split risking. So I'm going to take obviously the fan outline, and let's just go through an evaluation for reservoir presence. So at the shared level, what I've said here is that I've got an 80% chance that I have reservoir anywhere in this polygon. That's the question I answer. So I've looked at the seismic, I've made my evaluation, I've done my comparisons with other things in other areas, and this looks like a sandy fan. On the edge I'm saying it's 50, and in the abyssal shales I'm saying there's a 20% chance of sand. My local risk, the question I ask myself here is, if I've already found reservoir and I drill 100 wells, how many of those wells will continue to find reservoir? In this case, I'm saying 60 out of 100 will continue to find reservoir. And this is data dependent. This will change if I've shot 2D versus 3D, or I've improved the quality of my seismic. So this is, the best word to think of here is repeatability. How often am I going to repeat my success for this particular risk element? So when I multiply these two numbers together, I end up with about 50%. And if I had prospect standalone assessments here of reservoir present at B and C, these two prospects, I would expect them to be plus or minus 50%. Not exactly 50%, but on average in this polygon, I would expect all of my prospects to be plus or minus 50%. So that's my evaluation. As long as I've done my QC here and my prospect risking is roughly the same as my overall average risking, I've QC'd things and I've split my risks. So if I now come and drill prospect C, this one here, and I found sand, then I now have proven reservoir in this polygon. It's present somewhere in that polygon. My repeatability hasn't changed unless I've shot new seismic or done some reprocessing. So now my overall prospect risk, my average prospect risk, has gone up to 60. And you can see here that prospect B, even though I haven't drilled it, has had a relative increase in that prospect assessment. So the trick here is understanding that all we're doing here is providing linkages through this shared play evaluation between real prospects. And we can do that before we drill. So we don't need to drill these things and do it. We can do all of the evaluation for every play map before we drill. And that's what this figure is trying to explain. If I take an individual target in a play, and all of these leads and prospects are all in one play interval, that particular thing in black is in a charge polygon, it's in a seal polygon, and it's in a reservoir polygon. And obviously there's other polygons, but these are the polygons that relate to this single black target. Now, to keep the numbers simple, if I had a play risk of 50 for seal, 50 for reservoir, and 50 for charge, then in this common risk segment area in here, where the prospect is, 50 by 50 by 50, this will be 12.5% play risk. So if I came and found reservoir in here, or I made a discovery in here, then this play risk would go to 100. And these two prospects here, the play risk would go from 12.5 to 100. They would go up by a factor of 8. So if you follow the logic of what's going to happen now, obviously the overlapping areas, this one here between seal and reservoir, this one here between seal and charge, and this one here between charge and reservoirs, there the 50% will go to, it will go from 25 to 100, and everything will go up by a factor of 4. And these single areas where I've got a single risk, out here the charge risk is going to go from 50 to 100, and these prospects are going to double in their probabilities of success. So I can do this assessment before I drill any of these prospects, and these prospects outside are going to be unaffected. If I drill the black one, it doesn't affect these ones out here. And obviously if I now want to evaluate a different prospect, this prospect's going to sit in different polygons and it's going to touch different other ones. So this is the process we go through, and we can make a simple histogram in Player showing the risk volumes in black in here. This is obviously the biggest one. The impact through the common risk segment, which is this area in here. And then the grey area is the impact in the halo, which is all of these other areas put together. That's just to give them a nice simple name. We could give them different names, it would be very complicated. And what we can see here is that in a spreadsheet portfolio world, economic rationalists would want to drill this one here. That has the highest risk volume. But when we look at these prospects, we can see there's a couple of these prospects, maybe 3, that significantly de-risk other prospects. And even though we're drilling sub-economic probable volumes here, the impact of that success is so large, these are actually interesting prospects. So I'm not saying that you have to drill those prospects, but now you can have the conversation with your management. Do they want to play for something safe with very little impact on the portfolio? Or do they want to drill something that may be inherently more risky in terms of an individual target, but if it works, it's going to de-risk a whole bunch of other features. So again, this will change what you drill. If you're in growth mode, you're going to want prospects like this to develop your portfolio. And it's very simple mathematics, but this cannot be done in other platforms. This is what ARC does well, and nothing else can work with polygons like ARC. So none of the other platforms can do this calculation in an easy way. So what we're really trying to do is, the plays are groups, and you're trying to decide which one of these plays you really want to head down. If I drill a definitive test here and it fails, I might chop this whole branch off. And everybody has a tree analogy for play-based exploration, and this is mine. So it's a very, very simple concept. It's how you do it in reality that makes the difference. So when we look at those 3 different types, we've got the traffic light Goldilocks maps, the average prospect maps, and the split risk maps. And it's the split risk maps that give you all of those elements. You can measure the impact of each prospect on each other on success. You can define the play fairways areas in complex areas. There's a direct link between the prospects and the maps. And we always recommend geological boundaries, and all of them give you spatial insight. The key takeaway here that is in most cases you're going to draw very similar polygons between traffic light maps and split risk maps. They're not going to be that different, and in many cases they may be exactly the same polygons. So the only difference between the traffic light map and the split risk map is instead of putting one color in, you're putting in 2 numbers, and that's the only difference. So once you learn how to do this, people very rarely go back to traffic light maps because there's not that much work involved in going through to split risk mapping. So there's no correct way to do play analysis. We don't tell you what you have to do, and in fact in Player, in the one project, you can start with traffic lights in one area and go to split risks in another, and when you make your products, you can actually do a composite stack that is a split risk stack, or you can make a traffic light stack. So you can still go back to make the products that traditionally your management might want to see. But you've now got a lot more insight and useful products if you're using split risking, if you want to. So let me talk a little bit about seismic amplitudes and why I don't think they're going to be the silver bullet for exploration in mature basins. So I presume that most of the people listening are familiar with amplitude-supported exploration. There's lots of fantastic examples of how it's worked. My personal experience, though, is that because we often publish the good ones and we never talk about the bad ones, maybe it's just my bad luck, but I've been associated with a lot of amplitude-supported wells that have failed. And that's fundamentally because even if we have a well that's relatively close by in exploration, maybe 1 or 2 kilometers, there's still sufficient geological variability such that the reservoir and seal interface predictions can be quite variable. So without that really good control, it's very, very hard to calibrate the presence and particularly the phase of hydrocarbons. But when it does work, it works fantastically, and I understand why people love this. This is what managers and portfolios dream about. So if I take as an example the large discoveries that I know about around the world in the last decade or so, and I plot them, I basically divide them into two different types. So here I've got a schematic creaming curve. So this is discoveries that found the first big discovery in a basin. And then traditionally the cumulative volumes will then go up and then it will go flat. And at some point we'll call that basin mature. And in those mature basins, we are looking for big discoveries. We'll find lots of small things. Many of them will be sub-economic. But what we're looking for are big discoveries in mature basins. And these are very profitable because we normally have facilities and development opportunities in these locations, which means we can make a lot of money very quickly. These frontier ones, they're still very valuable in many cases, but quite often they're less valuable because we have to put in the infrastructure. So if I take these two different sets of global big discoveries or famous discoveries, let's now color them up by which ones were amplitude supported or not. Now the ones in red there are amplitude supported. The ones in black are not amplitude supported. So I think you can see a fairly common theme, and clearly amplitude support de-risks frontier exploration, where charge is quite often the fundamental risk. So when you have that particular element, you obviously have de-risked and it's obviously looking good. But it's interesting that none of the big late mature basin discoveries are amplitude supported. So why is that? Well, the answer is very simple. After you've made a discovery anywhere on the planet, in the following 5 to 10 years, effectively every amplitude that people can find is drilled. So by the time you get into the mature basin, there may be small amplitudes or small things, but the really big things, the things that you're looking at, which are game changers, are all gone. So in a general sense, you cannot rely on amplitudes delivering these big discoveries in mature basins. It basically means we have to go back to the fundamentals of geological analysis and the basics, and that's really what play analysis is trying to do. The other subject I see a lot, which in many ways competes with play maps, is charge models. And I'll take you through some of the issues that I see and why I think many of them are dangerous and often wrong. So quite often I see this workflow in companies. People get seismic and wells, they map prospects, they do some kind of volumetrics and risking, and then they make decisions. And the key sort of evaluation element that goes into the sort of risking cycle here is the charge model, and it's typically a 3D charge model in one of the main packages. And I find this kind of workflow incredibly scary. So let me explain why. Well, first of all, the charge modeling software that's available today is impressive. Many of it is fantastic, and it's particularly impressive when things spin in 3D. And managers love this stuff. It looks good, you can show that hydrocarbons migrating, and it is fantastic. But in many cases, not all cases, in many cases, there isn't the calibration or the understanding behind those 3D spinning models. And many of them are poorly QC'd and poorly understood, especially by the managers which are actually trying to make the decisions. So there are some specific issues about the different tools, and everybody argues about which ones they like or don't like, and that's fine. There's one that actually doesn't even have transient heat flow, which is a fairly fundamental thing in most charge modeling packages. And that's used by about half of the industry today, which is incredibly scary. But beyond the actual specifics of arguing about widgets, there's a couple of generic issues with all of them which I struggle with, and that's fundamentally understanding migration and source presence. So let me talk about those two aspects. So if I'm migrating hydrocarbons from a kitchen along a carrier bed and I hit a fault, I now have to make a decision in my model what I'm going to do. Am I going to trap all of the hydrocarbons against that fault? Am I going to make the fault leak it all up, or am I going to make it transmissible? And this can vary by phase. This isn't just a single phase thing. Sometimes the oil is trapped and the gas leaks, etc. So it's more complicated than even I'm showing here. So now what the charge modeler does is he or she looks at the distributions of hydrocarbons, tweaks the knobs, and then basically matches the distribution, and it is an internally consistent model. And that's fine. I understand why they do that. But fundamentally, the message I'm trying to give here, that in my opinion, migration is an input into these models. It's not an output. So you have to calibrate the migration. The charge model is not giving it to you, or if it is, it's just a model, one of millions that could happen. And so the key element that you need is a QC'd hydrocarbons show database. And in many cases, what people use is full of rubbish for lots of reasons which are obvious to many people. So if I take a theoretical example here I have a source kitchen, and I'm going to migrate laterally away from there. If I put in a few discoveries and some wells with shows and some dry wells, what the charge modeler will do is they'll sort of put a bucket around the fields, and then they'll have some wells with shows, and then they'll have wells that are dry. And there's nothing wrong with that. That is an evaluation. It's internally consistent, and this is what happens in the real world. So that's fine. That's an evaluation. But what you actually also need to do beyond the QCing of the shows and the pools is actually understand why wells have failed. And this needs to be done on a map, not in Excel. And I've seen lots of different failure interpretations around the planet. And these change. Remember that you might have a well where you believe it's off structure, you acquire 3D and you find it's on structure, and now you believe it's failed because of charge access. So things do change. It needs to be dynamic. So this is our scheme. It's our proprietary scheme. So this is reservoir, seal, trap and charge. This was developed at Woodside and went off into the shell world about 15 or 20 years ago. It was developed by my team. So I've been following this particular schema now for the best part of 20 years. And behind this scheme there's more detail that I'm not showing, which is proprietary. And there's some real tricks around how to actually apply this in the real world. So when we take those basic elements, if all the elements are present, then obviously we have a discovery. If we have the trap present, the effective reservoir and effective seals, but no hydrocarbon accumulation, this is a charge failure. We call these dry valids. If we have reservoir or seal failure of any type, but we have a trap present, we call those dry failed. Now the dry fails are telling us nothing about charge. The discoveries and especially the dry valids are telling us a lot about charge. We need to know where they are, because they're telling us where we have late structures or a migration problem. The other failures are where sometimes we're not even sure if we have a trap. The trap is ambiguous, and quite often we've drilled a play interval where afterwards we believe we actually missed the trap. But in order to make an interpretation here, we need to have all four elements, and if any one of those elements is not, you don't have the information on it, you cannot classify what that play test is actually telling you. So we do this on a play-by-play basis in an evergreen database that you can actually keep and build through time, and this is capturing your corporate knowledge. So if I go back to that initial example with the 3 wells, the key question I would want to know when I was looking at this 25% migration evaluation is what happened at those wells. If they all TD'd above this play, then they actually tell us nothing about this play. There's no information at all. If they all penetrated the play but were all off structure, that also tells us nothing. But if they were all dry valid, say charge failures, then I now have to come up with an incredibly clever story as to how I can sneak charge through into these prospects, that these ones have all failed. So understanding well failures is not academic. It's a key not just to understanding why the wells failed, but also to then take that knowledge into the play evaluations and your prospectivity evaluations. This is the key data that you need to build into the play maps. So what we do in Player is that we do one of these per play interval, and we decide what the play intervals are. They're not decided by other people. You can set them up for your own projects. The penetration data you can then collate, and then you've got the post-drill analysis for each of the plays. And we use this data in 3 ways. Obviously on a well-by-well basis, we understand why things work and fail now, so we can tell a story. We then use that same data on maps. So obviously we take the reservoir data and we plot it on the reservoir presence map, etc., etc. And then we help constrain the risk elements maps from that data. And lastly, we'll use the actual collective data from multi-wells to actually calibrate the success rates and the volumes on a play-by-play basis. So let's be clear here. If I have 10 wells in a basin and I have 2 discoveries, then a lot of people say, well, I've got a 20% success rate, so my prospect should be plus or minus 20%. I mean, the logic is just wrong. If you have those 10 wells and only 2 wells drilled the middle Miocene and the 2 discoveries were in the middle Miocene, that play has a 100% success rate. So you cannot mix up your well success rates with your play-by-play success rates. They're totally different beasts. And so if you really want to calibrate your prospects, they have to be in a play, and you need to have evaluated your play, which is what we're doing here. So this is how you can actually calibrate the historical success rate for specific plays. And that is a much better process than any peer review process. Peer reviews are useful, there's lots of knowledge, but they're commonly wrong. We all know that the same group of people next week might come up with a different number, and we would all guarantee that a different group of people with the same prospect in 2 months' time would come up with another set of numbers. So the only way that you can actually calibrate your prospects, your volumes and your success rates of your prospects, your evaluations, is to look at your historical success rates of your drilled wells. So if we go back to that dummy example, I've got my source kitchen. If these wells on the northern flank here were all off structure, they're telling me nothing. I could have maybe migrated hydrocarbons miles away up here. My previous interpretation was totally wrong. And if these wells to the south down here were all dry valids, in other words charge failures, then clearly I have some kind of migration shadow or something happening on this side, and I have to honor that with my risking. So you need to incorporate a QC shows database and hydrocarbon database, and you need to understand why wells work and fail. And that is how you calibrate migration, and migration is an input into your charge models. The second major issue is source presence. As an industry, we are classically poor at predicting this particular element. Maturity is easy. We can do this with seismic two-way time data. Now, in some parts of the world where you're lucky and you have extensive marine world-class oil-prone source rocks, it's less of an issue. You can normally map them on seismic and you can normally calibrate them fairly easily. But I work in a part of the planet where we have lots of wispy ephemeral source systems, typically non-marine and deltaic, and I don't know 20 kilometers away from a well that's drilled the source section whether it's still there or not. These are typically seismically invisible and very difficult to quantify in a charge model. So what I see typically is that when people run a charge model in these kind of settings is they'll vary the source rock in the kitchen. They'll have lacustrine and different thicknesses of source rocks, and they'll have deltaic and sort of woody and different types and different thicknesses. But they never ever run a model that doesn't have a source rock present. Now that happens. I know of lots of kitchens in the Far East where the easiest interpretation for all the failed wells around the outside is that there is no source rock. So this does happen a lot, but you would never buy a car with no engine. So when you give a problem to a charge modeler, there will always be a source rock, and that's what happens. So the only way you can actually understand whether a source rock is present in a basin is by looking at the drilling results around that particular basin, or DHIs, etc. But it's not inherently given to you by the charge model. It's very dangerous. So I'm not suggesting that you don't do charge modeling. And in fact, I like to do 1D charge models. I think they're just as useful and much quicker than 3D. But I do believe that evergreen play maps with well failure analysis is the key element that captures your geological knowledge and then links all of this stuff together. So you don't have to do it, it's just charge modeling is not the answer. So now let's talk about the green blob problem, and the solution. So what am I talking about here? Well, in many explored basins, if you take a particular successful play interval, you'll end up with a large green blob around all the fields. And your manager will say, well, I could have drawn that 2 months ago. What are you telling me here? You're telling me nothing I don't know. And the key logic jump here is inside those proven areas where obviously they've had a lot of exploration. What you're looking for now is different trap tests. You're looking for different trap types. All of the simple bumps are almost certainly going to have been drilled, all of the anticlines and the tilted fault blocks, all of the positive features. And you're going to have to start looking for onlaps and subcrops and different types of complex traps because all the simple stuff has gone. So if you want to classify things in basins, you actually need 2 layers of trap description, and that's what we've got in Player. We've got the gross structural scheme, and that's a genetic scheme, and then we've got a published scheme which was published by Nick Milton and George Bertram back in '92, and that's where is the well on the prospect or on the structure. And these are flexible schemes. You set them up per project, and they are global. They're nothing to do with the Far East. They're equally applicable in the Gulf of Mexico as they are in South America or the North Sea. So, and these are user-defined. It's a very flexible schema. So the gross structures are just kind of what kind of beast am I actually drilling? Is it a diaper flank? Is it a horsed? Is it a drape structure? All the obvious things that we talk about as geologists. And then the Milton and Bertram scheme, and this is a summary from the paper. It's simply a set of letters, C, U, T, F are the main ones. Conformable, unconformable, tectonic, which is a fault, and then facies change. So simple anticlines are simply Cs. A tilted fault block is a CT, conformable and tectonic. And then if I have a divider, then I've got a base seal involved. So a low side closure, a buttress closure, where I don't have any rollover, is a C on T, because the fault's underneath. An onlap is a C on U, a subcrop is a U on C. So it's a very simple scheme, and you'll notice here we're not talking about how the structure formed. These are not compressional, extensional. This is just the geometries involved in describing what the surfaces are on the target. So this is particularly useful. If I take as an example here this thrust cord fault block, this is one gross structure. But if I look at location A, it's been drilled in a fault independent component. If I look at location B, it's within the fault dependent part, CT. And then location C is drilled on the onlap. So we can be very specific about what tests have drilled and what types of structures have been tested. And this is important in mature areas. You want to separate out the different tests so you can actually look at which ones have worked and which ones have failed for different reasons. So, for example, in the subsalt of the Gulf of Mexico, you would probably only use gross structure. It's very hard to see the details of what these structures look like because of the imaging problems. Whereas in the Northwest Shelf or parts of the North Sea or places that are very well imaged that have very similar structures over large areas, we would probably only use Milton and Bertram. You don't have to use one or the other or both. So it's your choice. You can use neither if you like. So the example I've got here is from projects that we've made over the last few years from open file data from Australia, from the North of Carnarvon. So we've got 17 different play evaluations here with all the discoveries and all the success rates and all the failure analysis. And I think we've now evaluated around about 800 wells, all the penetration data, all the failure analysis, everything. So I'm going to select one of those intervals. I won't tell you which one. And this is a summary of where that particular play has been drilled. And you'll see in the deep basin areas it's beneath TD. It's absent in many areas. And the yellow and green areas is where it's actually been penetrated. It's actually been drilled by wells. So we can then go through the failure analysis of those particular wells, and you can see why we put the blue rings around the charge failures. So we can see over here that we've already got some charge failures, which is suggestive of a charge problem over here in the Beagle. I can then take an analysis of a polygon of this data. In this case, it's all the data. I could select a different subset, and I can see here that for these particular wells, for this particular play, I've actually got about a 1 in 4 success rate. If I ignore the ones that were off structure or low confidence tests, then I go up to about a 1 in 3. So if I had prospects in this particular play, in this basin, I would expect them on 3D to be about 1 in 3. That would be how I would calibrate my prospects based on my historical data. But I could also look at what the elements were that failed, and you can see here I can start burrowing down into the failure elements. And this is how you calibrate your prospects. You calibrate them against well failure, play by play. You don't do it at the well level. So we've made some reservoir seal and other evaluations. This is a play stack, a split risk play stack. So this is a composite stack. And in this case, this is just a shared risk element. This is that. And this polygon here in green is where we believe all of the elements are present. So that's our green blob, if you like. It's a very large green blob. I'm not saying that there's reservoir everywhere and seal everywhere, but we believe the elements are present within that polygon. So if we now look at what's been tested just within that polygon, not these wells outside, because clearly these have failed for other reasons, but in the area where we believe that everything should have worked, what happened with these different types of traps? Well, we can look at the log normal distribution of the actual volumes that were found, and we can play some games with that. But more importantly, we can actually look at the success rate of these different Milton and Bertrand trap types. So the fault independent closures, the simple anticlines, were successful between about 30 and 45% of the time. The tilted fault blocks were less successful, around about 25%, and there's these more complex ones. But interestingly here, this is a buttress test. This is a low side fault block, and one of those has been tested in that proven area and it failed. But there's only one that's been attempted. Now, we know why that failed. We've looked at the well, and that particular trap type in this basin has examples in other plays where there's 80+ million barrels of oil. So if I was exploring this particular play, I would be looking for low side buttress blocks. They clearly haven't been targeted, and I understand why the ones that have been targeted have actually failed. So green blob exploration is about understanding the history of the traps that have been drilled, their success rates, and what else you might be able to look at. If I had a prospect type that wasn't represented on that graph, then I know that that trap type hasn't been tested. That is a new trap type. It's in a proven play interval, but it's in a new trap type. So let me lastly talk about yet to find, or WTF is its colloquial name. So if I take a basin with all of its potential undrilled, as I explore in that basin, the potential will decrease through time. At some point, hopefully I'll make a discovery, and then at some point late in the basin, I'll have a fairly mature basin. There'll be lots of exploration. Now the key point in the basin is when I make this discovery. As soon as that happens, the entire world wants to come in and pick up acreage. And at that point, when I've drilled some of the prospects, but there's lots left, I probably haven't mapped many of the prospects. A proportion of what is left has probably been mapped, the ones in yellow. Later on, when I get to the mature phase, I can probably map just about every prospect in the basin if I have enough data and time. But at this key point here, I need to make some decisions. Now my management want me to map every prospect and come back with a logical reason as to why they should bid on one block or another. But quite often that just takes too long. And if I do that, I'll miss out on the opportunities. So the reason we make yet to find estimates is to actually make these business decisions. We know that those estimates are going to be wrong, but we have to do something here to make these decisions. If we wait until we map everything, we miss the opportunities. So in most basins on the planet, we've got some map prospects and we're trying to fill in the gap of the things that we haven't mapped, except in very mature basins where we just map prospects like the Gulf of Mexico. So here, this is about 99% of the basins of the world. We've got real prospects and we have to make some guesses. So the way that we make those guesses, the best way of making those guesses, is making an estimate of the structural density and the average size. And this is a simple mathematics. It's been done for 50 plus years, where we simply take the feature density, the number per 1,000 square kilometers multiplied by the area gives me the number of features. You want a field size distribution of what you think you're going to find, which you can calibrate from the past. We typically use just a single number, and we have a high, medium and low case in our scenario roll-ups. And then the probability of success is where we use the play maps that we've just made. And these are using the total chance estimates, not the play or shared values. This is the total chance, which is why we have to make that estimate of that third stack. We have to include trap and other things in these things. We can't just use reservoir seal and charge, and we certainly can't use a traffic light stack because that's not even numeric. We need numbers in here. So this is a numeric estimate of the yet to find per polygon, which we can then roll up using the tools in ARC and Player. Now the other things we can do here is once we've actually got these maps, we've got a polygon, we can actually we can look at the risk volume and we can look at the play risk in this. So if my play risk is 50% and my risk volume is 100 million barrels, I know that if I de-risk that play, that my risk volume will go up by a factor of 2. So we can effectively calculate success volumes per polygon, and we can identify those polygons that have significant upside potential and those that don't from this analysis. And what a lot of companies do is they calculate what we call the dry hole tolerance. So if I drill 2 wells in this polygon, what is the probability that I'm going to actually de-risk that play? And that's a simple mathematical calculation which is very useful for basin entry decisions. So for us, yet to find is the summation of the risk volumes in my prospects plus an estimate of something else that isn't in my prospects, and this is going to change. It's dynamic. It's a mixture. There's other yet to find estimates, and these are the typical ones that people use, and everyone's going to have a creaming curve. There's no problem with that, except it's only predicting the known plays. Geochemical modeling estimates are probably the most dangerous. A lot of companies use them, but when you've got 90% losses of all the hydrocarbons that you've actually generated, it gives you some idea about the error bar that's going to happen at the other end. So the structural prospect density method is the best one, and when you go through all the pros and cons, which is what this slide goes through, the reason why the larger companies use this method is because it is spatial. If I say to my management there's 1 billion barrels to be found in this basin, they will ask me within 3 nanoseconds where. And if I don't have a map that shows where that 1 billion barrels is, it's a waste of time. Consequently, creaming curves are generally a waste of time. When I've got my structural density evaluations, even though they're guesses, I can actually point at blocks and say, well, I think it's here and I think it's there. So the spatial aspect of making these predictions is what you need in the real world, which is why so many companies use this approach. This isn't our idea, it's an old methodology. So for us, integrating real prospects into your play maps is key to estimating your yet to find and obviously your success volumes. And adding the pseudo prospects on top is clearly the best way of actually making that estimate. Every other method, even though you might do them, has some pretty major technical issues, particularly those based on charge models. So finally, let me just summarize. So I've gone through all of the major issues that generally come up when people talk about play-based exploration. I would summarize and say that Goldilocks maps and average prospect maps don't integrate prospects, play maps and portfolio analysis. They keep these worlds separate. If you want to actually integrate your prospects with your play maps and make some clever decisions, then you need split risk maps. So that's why we always talk about these, is because of the major benefits, and doing that easily is obviously what geologists want to do. So people say, well, how does this help exploration? Well, I think that what I always quote back to people is a Greek proverb, which is luck is when preparation meets opportunity. So for me, the preparation is the play maps. You understand what's worked and you know what hasn't and where. And really going through the well failure analysis is the bit that brings that into the play maps. Nothing else can calibrate them. And then when you go around and look at different opportunities, it might be in your portfolio or it might be in a data room, you're going to see a prospect. And now because of that preparation, you know why that prospect is special or different. You wouldn't know that unless you'd done this preparation. And sometimes you might have to look at lots of data rooms and lots of opportunities before you find that one magic prospect that you're looking for. So for me, when these two things come together, a good search team and a proper play analysis, this is the best combination for actually looking for good opportunities. So in other words, like most things, I think you make your own luck. And this is all basic geological evaluation. This is not really play analysis. This is just doing the basics in a way that kind of makes it all easy. So play mapping gives you spatial focus. It saves you time and money. When you integrate it with well failure data and a proper QC shows and pool database, it's generally better, particularly when you're predicting migration, than any other charge model that you can build today. And it's certainly a lot quicker. It also collects all of your corporate knowledge in a dynamic evergreen database. There's different types of play maps, but only the split risk maps give you quantitative play-based evaluations and success volumes. And in areas with complex geology, they'll actually tell you where the fairways are. So play maps can underpin spatial yet to find estimates in both frontier and mature basin settings. And in proven play areas in mature basins, what you have to focus on is trap types. And you've got to look for missed or unusual traps and look for those opportunities. At the end of the day, it's all about sifting through the geological data in a structured and thoughtful way. And it's people that finds oil and gas. Good software just helps. And Player, to date, is the only tool that does all of this in a way that a working geologist can actually work with, which is why we're so busy at the moment. So that was my presentation. If you want to know more, then this is my email address here. This presentation only covers a fraction of what we can do with Player. Obviously it's focused on the conventional and many of the topical discussions that people have around play analysis. And Jeff works out of Houston. I'm based out of Perth in Australia, clearly the centre of the universe. And Jeff's in Houston and works for Rose, and he's the person to talk to if you want to talk about some theoretical training. So thank you for your time. I hope you've enjoyed the presentation. Please send me an email if you want to hear any more. Bye-bye.